Okay, so we've been talking about waves and particles and how light, EMR, has properties of both. Okay, let's talk about some evidence just to recap. We know that light can reflect. That really seems to exhibit properties of things that are, say, particles. If I were to throw a ball at the wall, it would bounce off of it, right? That seems to indicate that light is a particle. But then, for a while, Sir Isaac Newton basically got it in his mind that no, light is a wave. No, sorry, it was the opposite. Isaac Newton thought it was a particle. And then a bunch of physicists after he died said, no, I think light's a wave, guys, because it can do things like diffract, refract, and interfere with itself. Until about the early 20th century, about the year 1900, when Planck finally realized the photoelectric effect principles and discovered that light actually seems to act also as a particle, where if you have an incoming wave of photons, it can actually kick electrons out, just like particles can. Okay? And that's what takes us to the year 1923. So I'm going to pick this up now. 1923, Louis de Broglie. I'm sure I butchered his name, but I'm going to call him de Broglie. He was a PhD student, and he had this weird idea. He said, okay, everybody seems to be under the impression that light is both a particle and a wave. He said, what about the opposite is true? What if particles, things that we know for sure are matter, things like this desk, that chair, you and me, we are clearly made of particles. He suggested, what if those things actually had wave-like properties? Right? So light, which we thought was a wave, there's evidence that it acts like a particle. He suggested, what if clearly particle things, guys, what if clearly particle things acted as a wave? And basically everybody in the scientific community said, this is stupid. Like, that water bottle does not emit waves. We would detect them. And then eventually someone sent a copy of his thesis to Einstein. And I mean, that must have been the most validating thing in the world, to have somebody send your thesis to Einstein and everybody else says, no, you're dumb, this is wrong. And Einstein looks at it and goes, he's right. Like, how cool would that be? And Einstein agreed with him. And so here's what de Broglie basically did. He combined two formulas that we know. You guys should recognize this first one. It's for momentum, but more specifically momentum of a particle, right? Anything that has mass, like in our first unit, there's a way of calculating momentum. And here was a second formula, which we learned more recently, that anything with a wavelength has momentum too. Photons have momentum. You just have to take Planck's constant and divide by the wavelength. Well, he basically combined these two formulas because they both involve P. I don't know why the thing's spinning there. They both involve P. He put them together, rearranged it, and figured out that he believes that matter has a wavelength. This wavelength right here, and it's really based on three things. One, Planck's constant. Two, the mass of the object, which is supposed to somehow have a wavelength. And three, its velocity. Okay. So what de Broglie basically hypothesized then is that water bottle right there doesn't have a wavelength because it's not moving. But he suggested that other random matter things, they give off wavelengths. Like when I'm moving right now, I'm giving off a wavelength, which is kind of weird because what wavelength am I giving off as I move around? X-rays, radio waves? Like, it made no sense. But they were actually able to calculate these things. And I want to do a quick example here. Let's try to figure out what the wavelength of a 200-gram ball would be if it was traveling 15 meters per second. And we'll use this to get some perspective. So the formula was wavelength equals Planck's constant divided by its mass times its velocity, which is basically, this is its momentum. So you can treat it as the wavelength is equal to Planck's constant divided by the momentum. So what is Planck's constant? 6.63 times 10 to the minus 34. The mass of the item that we were using was a 200-gram ball, so 0.200 kilograms. And if it's traveling at 15 meters per second, what de Broglie hypothesized is that this item here is actually emitting a wave. So one more time from the top. Everyone else seemed to be in agreement that if light, which is clearly a wave but also a particle, if light can bounce between particles and waves, why can't matter also bounce between particles and waves? So I'm going to try the calculation here. 6.63 times 10 to the minus 34 divided by 0.200 and also divided by 15. I get this answer right here. 2.21 E minus 34. And that would be meters. Just want to give a second for anybody who wants to try calculating this. Try that as well. You guys okay? I want your focus today. This is a really cool lesson here. I know we're working into it, but this is such a small wavelength that although de Broglie and Einstein agreed that just any old matter must give off wavelengths, it's so small we cannot even detect them. I'm going to fast forward in a slide to this one right here. Here is a picture of like the wavelengths that we have here. And remember how visible light goes between about 700 to 400 nanometers? So that's like 400 E minus 9. Even gamma rays, way over here, gamma rays, the smallest thing we know of, they have a wavelength that's only to about the power of negative, I think that's negative 12 or 13 somewhere there. Well, what de Broglie calculated is something to the power of negative 34. Like, it's not even in the same ballpark. And that was the problem, is that they had no way of finding experimental data to support it. So Einstein agrees, yeah, I think that regular everyday life, I throw this up in the air, a wave just came off. It's like, but how do we detect it? It's even smaller than X-rays, gamma rays, or cosmic rays. And so there was actually a problem, is that the masses are too large. Because consider this equation right here. We can't really change Planck's constant, right? Planck's constant kind of is what it is. And velocity right here, velocity does have a capacity, right? The fastest something can travel is the speed of light. But the one thing that you can mess around with is mass. And this number right here, when we talk about everyday life stuff, is relatively large. So someone had a bright idea. He said, well, what if we found a mass of something really small? Like really, really small. So what is the smallest element? Hydrogen. Okay? And we now know that hydrogen is actually made of subatomic particles, electrons, protons, and neutrons. Someone suggested, well, what if we start firing electrons? Electrons are basically the smallest thing we can think of. How would that change if this number here was like 9.11 E minus 31? That's what we're going to do on the next slide here. Let's try to calculate a wavelength that would be given off by an electron traveling through a 100 volt potential difference. Maybe this would then be something we can detect. So let's use that same formula. The wavelength of matter is equal to Planck's constant divided by its mass and its velocity. The formula I just gave you. Well, Planck's constant, as it always is, 6.63 times 10 to the minus 34. Mass of the electron, 911 E minus 31. There is one piece of missing information here. How fast is it traveling? I didn't give you that speed, did I? Well, no, because I didn't say it was traveling the speed of light. That would be its capacity. It can't go faster than that. Where's the 100 volts come in? I just kind of threw an extra little twist in here for problem solving sake. How can you take a voltage and try to convert it to a velocity? Why don't I just pause there for a second and let you guys ponder that? Rather than me like give away the answer. If you think you have it, maybe just try it real quick. Because I want everyone to try to think through this problem. How can we turn a voltage into a velocity? Don't yell it out if you think you know it. Just so everyone can try to think of that on their own. What was that? Oh, I thought you said something. Okay. Okay, so there's not a lot of formulas that involve voltage on your periodic table. But hopefully you'll recognize one. Voltage can be found by finding the change in energy per charge. Hopefully you came across that one at some point, right? Okay, well, energy doesn't actually involve velocity yet, but its change in energy really isn't that going to be its change in kinetic energy? So you can make that 1/2 mv squared. So I can kind of like piece together a formula that looks like this. The voltage will accelerate the electron. I know it's mass, right? We're using mass again. Its velocity I'm going to solve for. And then charge, well, isn't the charge of an electron? So I threw a little twist in there to not make it quite so straightforward, but ideally that's like some sort of problem solving you can do. So let me find that velocity here. This will be 100. This will be 911 e minus 31. That'll be v squared all over 1.6 e minus 19. We just need to solve for the velocity now. So calculator time. Oh, square root. I got 5926, something like that. 5.926 e 1, 2, 3, 4, 5, 6. Anybody else trying this in the calculator get that value just so I know before I move on? Wow, yeah, you're right. I'm gonna store this in my calculator. That makes sense. So I'm gonna store this as A. Yeah, you're right though. I would round it up. You got that value then, I'm assuming? Okay, so let's plug that velocity in right here. So with that little side task kind of put aside here, let's calculate what the wavelength would be of an electron traveling really fast. So 1, it's traveling fast, but 2, it has a really small mass. Maybe this will actually give off a wave that we can notice. Okay. So 6.63 e minus 34 divided by 911 e minus 31 divided by that answer. And now I have the answer of 1.23 e minus 10 meters. Well, this actually comes full circle now. At the very, very beginning of this unit, we talked about some requirements for producing electromagnetic radiation. What is the requirement to get electromagnetic radiation going? Well, electromagnetic is electric and magnetic fields, right? But what creates the initial magnetic field? A moving, charged particle. Remember talking about this? If you ever have an accelerating, moving charged particle, it creates EMR. That's how our light bulbs are working right now, by the way. Right? Electrons are running through these light bulbs. They are being accelerated across a gap, and in doing so, they're giving off EMR in the form of, yeah, like what you're doing right there. The electrons are oscillating back and forth at a certain frequency, and in doing so, they're giving off a form of EMR. The particular form it's been set to is visible light, so that we can actually see them, right? Well, now, this electron right here, it is actually producing a wavelength, which actually makes sense. We kind of knew this. Now, in 1923, they didn't, by the way, right? But we now recognize that, yeah, when you have accelerated charged particles that give off EMR, and we can actually tell that EMR, we can actually quantify it. It is literally how an X-ray machine works. An X-ray machine, what they do is they shoot electrons at a sheet of metal. And ideally, the electrons go slamming into the sheet of metal, and they rapidly decelerate. And as they rapidly decelerate, they give off EMR because they're changing their velocity. Does that make sense? So anyways, long story short, we can actually detect this wavelength off of matter that is either quite small or matter that is maybe traveling at high speed. This one really does both. It was both small and traveling quickly. Now, if I want to go to the electromagnetic spectrum, the answer we just got there was 1.23 e minus 10. I mean, that's basically right about here. It's in the ultraviolet to purple to X-rays kind of spectrum, somewhere in this area here. So we can actually detect that sometimes, and we've actually made devices intent on doing that, like an MRI, magnetic resonance imaging. Oh my gosh, I can't say it right. Right, where it's actually based on using X-rays from like magnetic fields being given off. Okay. Here's where my lesson stops, and now I'm going to show you a bunch of YouTube videos. They were challenged to try to measure the wavelength of an electron, and it is very small, so it was challenging to measure it, but we've now gotten better at that. But there were some other implications that came up, and so I want to show you some YouTube clips, and we'll talk about each of them as we finish. So I'm going to stop the video now.